So let's look at the last section in this unit, and just to remind you where we've been is we dealt with proportions, we've dealt with means, and now we're dealing with variances. And now we're going to look at how do we look at two variances or standard deviations. So what we're going to do is we're going to look to see if the variances or standard deviations are the same. We're going to do an F test. You can see it's named for Sir Ronald Fisher. Now, one of the things that's extremely important is that both populations need to have normal distributions. These tests are very sensitive. So if you have even a slight variation from normal, you're going to do the Levine-Brown-Forsythe test, which is a little bit more robust against departures from normality. We're not going to deal with those tests. If you are in a situation where you need to do an F test, you will have taken more statistics and you will have access to a statistical advisor who will help you do this. So what we're going to do is we're going to test a claim about two population variances or population standard deviations. Okay? And just remember that our variance, which is sigma squared, is our standard deviation squared. So that's for the population. So that's our parameter. And remember, our statistic will be S for the standard deviation and S squared for the variance. So we always take population 1 to have the larger of the variances. And so we're going to look at the sample variance, the sample size, and the population variance. And then we use the same symbols for that second sample. So it's important that the two populations are independent. It's important that they are both simple random samples, and they must be normally distributed. Now, must. They're not robust. They don't work if it's non-normal. So, must. So the F test is simply a ratio where we take the first sample variance divided by the second sample variance. And what we're going to work through in these slides are how to do it with the tables. And you'll find those F tables, and they're also in Appendix A in your textbook. And if you have the 13th edition, those F tests will be Table A5, which are on page 690 and 691. If you use the tables, you have to use a range of p-values. So here's the deal. We're going to use technology. So in other words, I'm going to show you how to use the table just so that you get an idea of what we're doing. But we're going to use StatCrunch to do it. So I recommend that you practice using StatCrunch. Look at those end of the chapter, end of the section problems, and the end of the chapter problems, and pick some out that are going to be appropriate. And remember, the answers to the odds are in the back of your book. If you do an even and you want to know the answer, you let me know and I'll get you the answer. Okay, so the first thing we're going to do is we're going to look for our significance level. And that is along, if you look at Table A5, our significance level, we have two tables. So on 688 and 689 is for alpha equal to 0.025 in the right tail. On the next two pages, 690 and 691, then we have alpha equal to 0.05 in the right tail. We're going to have 2 degrees of freedom. And so we look at the numerator degrees of freedom, and we look at the denominator degrees of freedom. And so the numerator determines which column of table A5 we're going to use, and then the denominator, degrees of freedom, determines the row that we're going to use. If we have a two-tailed test which is not equal to, then we're going to use the first 2 pages. If we have a one-tailed test, we're going to use the second 2 pages. And what we're going to do is we're going to find the critical value. And if you remember from our previous discussions, that critical value is the boundary between statistically significant and not statistically significant. We're going to have 2 normally distributed population. We're testing to see if their variances are equal. So we're testing to see if the test statistic is close to 1. So one of the things that's true about the F distribution is it's not symmetric, and there are no negative values. And again, that exact distribution, the exact shape, depends on our numerator and denominator degrees of freedom. So again, if the 2 populations have equal variances, that ratio will be close to 1. If they're far apart in value, then our F will be very large. So again, an F value near 1 is evidence in favor of our null hypothesis, but a large value of that ratio is evidence against our null hypothesis. So here's some data, and we have populations with the same mean. These are evaluation scores of female professors and male professors, and we think they have the same variation. So here's the deal. Notice that our numbers are different in our 2 samples. Evaluate the descriptive statistics for both samples. So first, are the 2 populations independent? Are they matched? Well, no, they're not matched. They're independent. You can't have anybody in both samples. And then we're going to assume there's simple random sample. That's from the design of the study. And then it does show that both samples appear to be from populations with normal distribution. So we're good to go. So here we go. For the female professors, we get the standard deviation of about 0.56. For the males, we get 0.39. So that means that the female professors will be sample 1 and the male professors will be sample 2. Okay? Now, this is not correct. If we're going to square these, we'd have to square the numbers. Let's see if they fix that in the next slides. So, our null hypothesis is going to be that they're equal, and then our alternative is not equal. So we're going to use those second 2 pages in our A5 table. So here we go. Now here they're doing it. They're going to square those numbers. So let's go back to that previous slide just so that our math is correct. Oh, they did have the square in there. I'd like to see those parentheses so we don't miss it. Phew. Now we're going to do that math and we get an F statistic of a little bit more than 2. Now what does that mean? Well, we are going to look at the numerator. Degrees of freedom is 11. And our denominator, degrees of freedom, is 14. And we're going to find the critical value for these 2 pieces. And I'm going to pull that table in so you can see it. So since ours is a 2-tailed test in that we have our alternative is not equal to, we're going to use the part where we have alpha equals to 0.025 in the right tail. Now, if you remember, our degrees of freedom were, our numerator degrees of freedom is 11, which is in between 10 and 12, and our denominator was 14. So our critical values are going to be between 0.31469 and 0.30502. So that's how they get those. So we use the 14 column, and then we need to use right in between here. So that's how we get those two numbers. And so our F statistic is less than our critical value, so the area to the right of the tail is greater than 0.05, meaning that our p-value will be greater than 0.05. And when our p-value is greater than alpha, it is not statistically significant. So here is our critical value. Here is our test statistic. Our test statistic is not further out in the tail than our critical value, so it does not fall into the critical region, meaning that it is not statistically significant. Not statistically significant. There we go, two S's. We fail to reject the null hypothesis. There's not sufficient evidence to warrant the rejection that the two standard deviations are equal. Now, I would like to take this one more step because we need to have it in language that we can understand. The course evaluation scores of female professors and male professors appear to have the same amount of variation. That is a really good summary statement. It doesn't have a whole lot of statistical jargon in it. We're going to use StatCrunch to do this problem. If you have the 13th edition, this is in your book at the end of section 9.4, but it uses the data set in the back of your book. And so we are going to look at the weight in pounds of cans of regular Coke and cans of Diet Coke. We want to test the claim that the variation is the same for both types of Coke. And here are the directions for StatCrunch that are also in section 9.4 in your textbook. So let's go on and let's pull up a whiteboard and StatCrunch and work through the problem. Okay, let's do the Diet Coke problem, and let's start with our format of our 6-step test. And so our first step is going to be our hypotheses. Our null hypothesis is that the variation of Coke equals the variation in the weight of the Diet Coke cans. Now, on StatCrunch, they're going to talk about this as a ratio. And so if this is true, if they're equal, then that ratio will be 1. So these are both alternative ways to write your hypothesis. Then our alternative, because the problem doesn't say a direction, just are they the same or are they different, we're going to say that the Coke is not equal to the variation of the Diet Coke, or continuing the pattern of the ratio, the variation of Coke over the variation of Diet Coke is not equal to 1. Okay, we're going to set our alpha, and we're going to summarize our data just so that we have it handy. So when we have Coke, there's 36 cans in our sample. The mean weight of the can is 0.8 0.1682 pounds. And our standard deviation is going to be 0.00751 pounds. Our Diet Coke, there's also 36 in the sample. The mean weight of our Diet Coke cans is 0.78479 pounds. And the standard deviation of our Diet Coke is 0.00439 pounds. Okay, now in your book it said that the larger standard deviation is always your group 1. So that's going to be our Coke, and then our Diet Coke will be group 2. So now in step 4, we're going to write the formula of what we're going to do. We're going to use an F test. And our F ratio is our variation of sample 1 over our variation in sample 2. Okay? Now, this is where we're going to go to StatCrunch and actually do the math. So let's do that. And so I'm going to go to Stat, and I'm going to do variance statistics to sample, but I'm going to go down to with summary. All right, and let's go ahead and let's put our data in. So our variance was, oh man, we've got to square that. So let's go back. I'm going to square 0.00751, and you can see what I get. So now let's see if I can cut and paste that. Copy, and let's go back to our whiteboard. Nope, sorry, we got to go back to our StatCrunch, don't we? And let's see if we can paste that. Yay, it works. Our sample size is 36. Let's do our variance for the Diet Coke. And that's going to be 0.00439 squared. Let's copy that. Go back to our StatCrunch, paste that in, and my sample size was 36 again. My null hypothesis is that they're equal, so it's equal to 1, and my alternative was they were not equal, so then the ratio would not be equal to 1. I'm going to compute. And there I have my statistics. So there's my F statistic right there and my p-value. Let's see if I can copy this. And I'm going to take this back to my whiteboard. And let's see if I can paste it in there. No, so let's undo that. So let's go back to StatCrunch. Oh, an easier way to do it than to do all that is I have my snipping tool on my toolbar, and I'm going to use that. And I'm going to snip my results. And I'm going to copy this. And I'll take that back to my whiteboard. And there it is. I'm going to make it just a little bit bigger so I can actually see it. So there is my F statistic, 2.9266551, and my p-value. Now this is where we need to then finish up. So remember that if my p-value is less than alpha, then this is statistically significant. And that is true because 0.002 is less than 0.05. So that means in step 5 we can reject our null hypothesis. And then in step 6 we need to put it into everyday language. These data suggest that the variation in weights of Coke and Diet Coke is not the same. Okay, and we're done.